Hi, welcome to this penultimate chapter of Discovering Design with Physics from Berean Builders, the chapter 15 review questions. So we're going to skip number 1 because that's a definition question and we can quite easily get that from the book. Question number 2, I'm also going to just refer you to go back and look through the chapter. If you don't know the answer to any of these, just find the diagrams in the chapter and then read the parts that are describing each diagram, and you should be able to figure those out for number 2 pretty easily. So now let's talk about number 3. For A, we're looking at the circuit shown right here, and it says through which resistors is or are current flowing as it is drawn. So as it is drawn, there are 2 open switches, and in order for current to flow, we need to go using conventional current from the positive to the negative side. And so you can see here, just because this first switch is open, we can't complete anything. There's no way to get back to this negative side. So for A, neither of these resistors has current flowing through it. For B, through which resistors is current flowing when S2 is open but S1 is closed. So if S1 is closed, the current is then able to go through this 15 ohm resistor and back to the negative side, but it's not able to get to the 25 ohm resistor. So for B, it is going to be only the 15 ohm resistor. That is the only complete path from positive to negative. For C, through which resistors is current flowing when S1 is open but S2 is closed. Okay, so then again, if S1 is open, we are coming from this positive side and we stop right there. There's nowhere else it can go. And so just like A, neither resistor is going to have current flowing through it because when S1 is open, even if S2 is closed. And then finally, D, which switches should be closed to produce the lowest resistance? Okay, so when if S1 is the only switch that is closed, then our resistance would be 15 ohms, all right, because that's the only resistor that it is going through. But when both of them are closed, we have a parallel circuit between these 2 resistors, and that's always going to result in less resistance than either one of the individual resistors. For question 4, we have the circuit on the right, and suppose S1 is closed and S2 is open. I'm going to just draw this. S1 is closed, S2 is open. If the battery shown is 9 volts, what is the current that flows from the battery? Okay, so we have a resistance here. Well, let's just look at what's going to happen. So positive to negative, it's only going to go through this resistor because S2 is open. And so this is our only resistance that is going to happen, and it's just going to go to the negative there. And so our resistance equals 15 ohms, and our potential difference is 9.0 volts. Okay, and then we can use Ohm's law, which is our equation 15.1, that our potential difference equals the intensity of our current times our resistance. And this is just a little side thing. I always like to know, like, why did they choose the abbreviations? Well, they couldn't really use C because C is used for capacitance already. And so what I actually stands for is it's French, and it stands for intensité du courant, which is the intensity of the current. So just FYI, and if that helps you remember what that I is, then that's great. Okay, so we're going to solve for I because we are trying to get the current. And so I equals V divided by R. Okay, and so our voltage is 9.0 volts divided by our resistance, 15 ohms, and we're going to get 0.60 amps. Now, one of the things that drove me nuts in this chapter is that we've spent all year long making sure that we can cancel our units to check our work. And in this chapter, it's kind of thrown out the window. It's just as long as you have the correct units for the correct variables, you just go with it. And honestly, like, it struck a nerve with me, and I was like, oh, I don't want to do that. But seriously, if we were to convert all of these units into things that we could easily cancel out, it would be so complex and such a headache that Dr. Wile is right for this chapter. It is very much simpler and easier to just trust him and just make sure that you have the correct units in the correct place. So our final answer here is that the current is 0.60 amps. Okay, for question 5, if both switches in the circuit drawn above are closed, so now they are both closed, what is the effective resistance of the circuit? So at this point, now we have a parallel circuit, and so we're going to use equation 15.5, which is about having resistors in parallel. And we need to find what this effective resistance is. And so 1 over the effective resistance equals, and you have the resistor 1 and resistor 2. So 1 over 15 ohms plus 1 over 25 ohms. We're going to get 0.067 ohms plus 0.040 ohms, and that is going to give us 0.107 ohms. And remember that this is not our final answer because this is 1 over the effective resistance, and we need to get the inverse of this. So we'll do that. And so the effective resistance equals 9.35 ohms. Okay, for question 6, for the circuit shown on the right, what is the effective resistance? So pretty simple here. We have a circuit that is in with resistors in series, and so for that equation 15.4, our effective resistance equals, and we're just going to add up the resistors without having any fractions. So 15 ohms plus 25 ohms, and we get 40 ohms. And so now this is only showing one significant figure, and so we're going to just have to convert it in our answer. to scientific notation so that we show that we have two significant figures, because we do. So the effective resistance is 4.0 times 10 to the 1 ohms. For B, if it draws 160 watts, what is the current? Okay, so watts is power, which means that we're going to need to use either equation 15.2 or 15.3. And so we have the power equals 160 watts. We have that the resistance equals, I'm just going to write it in not scientific notation here, and I'm going to underline it for me, this helps me know that this is two significant figures. Okay, and that is all we have. So we need to figure out the current, and so that gives us 2 out of 3 for equation 15.2, which is Joule's first law, that P equals I squared times R. And we need to solve for I, our current. And so I is going to equal P over R. And we're going to take the square root of that. And so let's plug everything in. We have 160 watts for our power up top and 40 ohms for our resistance. And we'll be taking the square root of that. And so when all that is said and done, we get 2.0, having two significant figures, amps. And so the current is 2.0 amps. Okay, what is the voltage of the battery? So now we have two choices. We can use one of two equations. We have the other equation with power, equation 15.3, where power equals and the current times the voltage. And so we have power, we have the current, and so we can solve for the voltage. Or we could use equation 15.1, which is voltage equals intensity times resistance. So this is Ohm's law. Okay. Either one you want to use, I'm just going to pick one. Probably this one's the easier one to do, but because I had power in my head from doing the previous problem, when I did this, I went ahead and used the power equals intensity times voltage. You'll get exactly the same answer either way. So let's convert that to, or solving for voltage. And so voltage equals power divided by intensity. And so 160 watts divided by 2.0 amps for our current. And we get 80 volts, which again, we need to convert into scientific notation so that we have two significant figures. So the voltage is 8.0 times 10 to the 1 volts. For question 7, we have this circuit on the right, and we need to determine what the effective resistance is. So let's just, drawing from here, from the positive side, we come this way, and then we have two choices. We can go up top, or we can go down here. And here we also have two choices, and so there's two resistors that are in parallel. So whenever we're doing these, we need to add up all of our resistance and get a total effective resistance. And we have to kind of do this piecemeal because there are some parts that are in series that we can simply add, and then there's some parts that are in parallel that we need to get their total effective resistance first. Okay, so we have these that are in parallel here, and then once we get the sum of these, the effective resistance of these, then we'll have this effective resistance of these and this, and we'll have to get the effective resistance of those parallel. Okay, and then these two are ones that we have to go through to get from positive to negative, and so those are going to be our resistors in series. And as we'll do this, we'll change up our drawing to demonstrate what we're doing. So let's start with here. So we're going to use our equation 15.5 with resistors in parallel. And so we have 1 over our effective resistance equals 1 over, we have, I'm going to do the top one first, 7.0 ohms plus 1 over 6.0 ohms, okay? And we'll get 0.14 ohms plus 0.17 ohms. And we add those together, we're going to get 0.31 ohms. Okay, we remember that this is 1 over the effective resistance, so we need to get the inverse of that, and that will get 3.2 ohms. Okay, so that is what the effective resistance of these two parallel resistors are. Now, forgive my drawings because they are not going to be nearly as beautiful as in the book. I'm going to redraw this. Okay. And now, instead of having those two resistors in parallel, we've made it 1 in the middle. And I'm going to label it 3.2 ohms, 8.0 ohms up top. Okay, I'm not going to worry about these because we're going to end up redrawing those in a second. But these are the two that we're going to focus on now, because now these are in parallel and we need to get the effective resistance of the sum of these. Okay, so we're going to do the same thing there with the same equation. 1 over the effective resistance equals 1 over 8.0 ohms plus 1 over 3.2 ohms. And we're going to get 0.13 ohms plus 0.31 ohms. And that's going to give us 0.44 ohms. And take the inverse of that to get the actual effective resistance, and that's going to be 2.3 ohms. Okay, so the effective resistance of this is 2.3 ohms, and we can now redraw this again. And so we're just going to eliminate, and see, this is where I'm not good, the parallel nature of that, and just put, like it's in series, 2.3 ohms. Okay, so now I'm going to take these numbers that from up here, 5.0 ohms, and this is 9.0 ohms. Now we just have a circuit that has resistors in series, and we can use equation 15.4 for resistors in series to find the total effective resistance. So 5.0 ohms plus 2.3 ohms plus 9.0 ohms. And so our total there is 16.3 ohms. So the effective resistance is 16.3 ohms. For the B portion of this, we're using the same diagram, and we're asked what is the current in the circuit on the previous page. Okay, so for this we can use Ohm's law. V equals our current times our resistant, and we were given the voltage and we just determined the resistance, and so we just solve for current. So I equals V divided by R. Our voltage is 1.5 volts. And we're dividing by our resistance of 16.3 ohms. And we're going to get 0.092 amps. For C, how much power does the circuit on the previous page draw from the battery? So again, now we're looking at power, so we could use Joule's first law or equation 15.3. So Joule's first law is that P equals I squared times R, and we have two of the three, right? We have the current and we have the resistance, 16.3 ohms. And so you can use that one. Or we can do P equals I times V. And we can use that one too. We have I, 0.092 amps, and we have the voltage of 1.5 volts. So since equation 15.3 is a little bit easier because we're not having to square anything, that's the one that I am going to choose to do. So we have 0.092 amps times 1.5 volts, and we get, this is power, so we're going to be in watts, 0.14 watts. And just a note with, if you're using these same numbers, 0.092 for the amps and 16.3 for the resistance, and if you're using equation 15.2, P equals I squared times R, you should get the same number. For question D, suppose the device represented by the 7.2 ohm resistor in the circuit ends up breaking. Which resistors will still have current flowing through them? Okay, so I'm not going to write this one down. We'll just talk through it. So we're coming from positive. If the 7.0 ohm resistor breaks, we still have lots of options, right? It can still go through the 6.0 ohm resistor, or it can go through the 8.0 ohm. And so the resistors that still have current flowing through them are 5.0 ohm, the 6.0 ohm, the 8.0 ohm, and the 9.0 ohm resistors. So essentially, all of the other resistors besides the 7.0 ohm would still have current. For E, suppose the device represented by the 9 ohm resistor on the circuit ends up breaking, which resistors will still have current flowing through them? Well, because we have to go through this 9 ohm resistor to get to the negative side, the answer is going to be none, because if we can't go through this resistor, then there will be no current flowing at all. And so for E, the answer is none. For question 8, what is the purpose of a fuse? Okay. So a fuse, its main purpose is that it's going to stop current from flowing if it exceeds a specific value. It's there to protect the circuit and the wiring from having too much current flowing through it and becoming a hazardous issue. For number 9, how is a fuse similar to a circuit breaker? How are the two devices different? So they have the same purpose. This purpose is still to stop the current from flowing if it exceeds a certain value. But the difference is that when a circuit breaker exceeds that value, it flips and just turns off the circuit. Whereas a fuse, it is destroyed by the current when it exceeds that value. So a fuse, it has to be replaced by a new one whenever it blows. But a circuit breaker, of course, can be reused. If it flips open, we just flip it back closed. In the circuit, for number 10, in the circuit diagram shown on the right, indicate the positions where you could put in a fuse or circuit breaker so that it would stop all current from flowing out of the battery. So what we need to focus on is where we have things in series versus parallel, where current has to go through, whereas in other places it has a choice. Okay, so when this current goes from the positive side, it's going to have to go through this area. So we could put a fuse in any position here, right? It has to go through this area. So any position here for a fuse. Starting here, it has a choice, okay? And so we wouldn't want to put a fuse anywhere along here because the current could just skip that and go somewhere else, right? So coming back this way, after these parallel resistors, we're back in this area where the current has to flow. So a fuse could be put there, or it could be put anywhere along here, okay? So there are 4 different general positions that a fuse could be put so that it would stop all the current from flowing out of this battery. For question 11, we have this new circuit diagram. Says you have fuses that have integral values for current. In other words, they're integers, okay? So 1 amp, 2 amp, 3 amp, etc. What value fuse would you use? So what we need to first determine is what the total effective resistance is, and then use that to determine what current is running through this circuit. So we have lots of things that are parallel and in series, and so we're going to have to condense all of that down and so that we get one overall effective resistance. So Dr. Wile recommends starting always with the positive side and just running along, and wherever you reach parallel things, you start with that as far as consolidating your effective resistance. So we're going to start right here and get the effective resistance of these 2 parallel resistors, because that's the first thing we run into is this choice of going to the 2 ohm or 1 ohm resistor. So equation 15.5 does get our effective resistance of these resistors that are in parallel. And so we have 1 over 2.0 ohms plus 1 over 1.0 ohms. And I get 0.50 plus 1.0. Both these are in ohms. And with precision to the 10th place, we're going to get 1.5 ohms as this 1 over effective resistance. And we're going to take the inverse of that, and we're going to get 0.67 ohms. Okay, so that is what this is. So let's redraw. Okay, so lots of things going on here. Okay, so we got 0.67 ohms. That's what we consolidated this to this. Okay, then we still have these 5.0 ohms, 4.0 ohms, 3.0 ohms, and 6.0 ohms. Okay, so as we continue traveling up this circuit, now we have 3 choices of parallel resistors, and so we're going to get the effective resistance of these before we move forward. We'll have 1 over 5.0 ohms plus 1 over 4.0 ohms plus 1 over 3.0 ohms. We're going to get 0.20 ohms plus 0.25 ohms plus 0.33 ohms. And when we add all those together, 0.78 ohms. Okay, we're going to get the inverse of that. So we are isolating effective resistance, and we get 1.3 ohms. So that's our effective resistance of these resistors that are in parallel. So let's redraw this. And so we have 1.3 ohms, 0.67 ohms, and 6.0 ohms. So now we're going to, these are all in series now, so we can just add these to get the effective resistance of the overall circuit. And we'll get 8.0 ohms. So this is our overall effective resistance. And, you know, we could redraw this even one more time if you wanted to and make it a very simple circuit with a fuse and put 8.0 ohms right there. Okay, so now we have the effective resistance. We have a voltage that was given to us up here in the original diagram. And so we can use Ohm's law to find what the current is. Okay, so Ohm's law, V equals I times R. And so I is going to equal the voltage divided by the resistance. Our voltage is 25 volts and divided by 8.0 ohms. And we're going to get 3.1 amps. So we're still not at the answer to our question. The answer is what fuse should we use? Okay, and so they have integral values. So you have 1 amp, 2 amp, 3 amp. And so you want a fuse that is going to be able to cover this, but be as close to it as possible. So you're not going much higher than you have to, because if you go higher, the higher you go, the more danger there is of damage occurring in your circuit. Okay, so we can't use a 3 amp because this is a 3.1 amp circuit. And so we do go to the next highest integer. And so we would use a 4 amp fuse. And I put 0.0. You could just say 4 amp. The way this is written, you don't have to put 0.0. For B of question 11, we have what power does the circuit on the previous page draw from the battery? So again, we have a choice. We can use equation 15.2, Joule's law, with P equals I squared times R. We did just determine what the amperage was. So we have I, and we do have R as well. Our effective resistance is 8. Or we can use P equals I times the voltage. So we can use I, 3.1 amps, times our voltage of 25 volts. Again, since that second one, equation 15.3, is easier, that is what I chose to do. So P equals I times V. And so our I is 3.1 amps times our voltage of 25 volts. And with that, we will get 78 watts. Now on this one, I will warn you that if you do use the other one, which is perfectly valid, if you use P equals I squared times R, the answer is going to be slightly different. I got 77 watts for the answer using equation 15.2. But either way is acceptable, and either answer would be acceptable as well. So the power is 78 watts. For question 12 through 14, we're going to be using these circuit diagrams here. Question 12 asks us which one represents a circuit that has one resistor that requires more current than the battery can supply, and another one that doesn't require as much current. So for this one, it's going to be circuit C. So the first part of this question, a resistor that requires more current than the battery can supply, that means that we're looking for capacitors, okay? So both A and C have capacitors. That is this symbol here, okay? And so that's the way that we supply a burst of current that's greater than what a battery can supply. However, in A, both of these resistors can be powered by the capacitor, so they both get more current than the battery can supply. For C, however, one of these resistors gets current only from the battery, and that's this one here, while the other one can run with the capacitor. So this is telling us that this one can get power while this capacitor is charging, but this one most likely needs that quick burst of power from the capacitor. For question 13, assuming that each battery symbol represents the same amount of voltage, which circuit can have the largest amount of sustained current? Okay, so that would be circuit D. We have B and D both have 2 batteries. Okay, A and C only have 1. But B has the batteries that are in series, and D, they are in parallel. And so when you have batteries that are in parallel, that allows current to be flowing through here twice, right? And so that actually gives twice the current because there are 2 batteries going through there. For 14, assuming that each battery symbol represents the same amount of voltage, which circuit has the largest potential difference? So when we have batteries that are in parallel, they are both only putting out the same as one battery, right? So 1.5 volts, 1.5 volts, right? But if you have them in series, with that, you will be adding the voltage. So with B, that's going to be twice the voltage because we have 2 batteries. And so therefore twice the potential difference. And so the answer for 14 is that B gives us the largest potential difference.